Welcome to the beginning of right triangle trigonometry. Since we're starting our unit on trigonometry, it's probably a good idea to figure out what is trigonometry in the first place. Well, it's the study of how angle measures and side lengths interact in a triangle. Now we're going to focus specifically on right triangles for a while. So remember, a right triangle has certain key components. There's a single right angle, which is often labeled C. Two legs, these are the sides that make up the right angle, usually labeled A and B. I like to think altitude and base. And two acute angles, because these two angles here and here are sharing the other 90 degrees that make up this whole triangle. And C, the long diagonal length called the hypotenuse. Now, if any of these sides were to change, then theta and alpha, two symbols we use for angles, would have to adjust because this right angle is fixed. So imagine stretching side B out longer. Angle theta would have to get smaller. Angle alpha would actually get bigger, and side C would have to stretch out too. So as it turns out, anytime you mess with a side or an angle, you're going to cause some changes in the triangle. If any one of the acute angles is changed, that will go along with the change in two of the sides. So let's think about if any two sides could result in a change. And because the change in size in items in a triangle is usually done by a ratio, let's think how many different ratios could you make using these three sides? There are 6. I could do A with B, A with C, and B with C, but then I could do the reciprocals of all of those, because we know that division is not commutative. A divided by B and B divided by A are two different things. Well, in the world of trigonometry, since each of those ratios could be a different number value, each is given a special name when we talk the relationship between these ratios and the angles in the triangle. These form the 6 trigonometric ratios: sine, cosine, tangent, cosecant, secant, and cotangent. So now let's look at this more closely so you can see how it all operates. We're going to start with one of my favorite right triangles. This is the 5, 12, 13 right triangle. Here's theta. It really doesn't matter which angle we look at, but it's important to label that because every ratio in trigonometry is built by looking at the triangle from the perspective of theta. So everything I'm going to do depends on standing right here in angle theta. Now, to theta's perspective, the 12 is what we call the side opposite, because you can look right across at it. To angle theta, 5 is the side adjacent. It's right next to it. And to angle theta, 13 is the hypotenuse. 13 is the hypotenuse no matter what, because it is the long diagonal side. Now, if you remember, there were 6 ways to make the ratios, and each one has a name. So let's look at all 6 from this right triangle. Sine, abbreviated SIN, the sine of theta, is the ratio that compares the side opposite to the hypotenuse of the triangle. So in our example, that's going to be 12/13. In case you're wondering, what is that number going to mean? Don't worry, we're going to get to that. For now, we're just trying to build the ratios. Cosine theta, abbreviated COS, compares the adjacent to the hypotenuse. That would be 5/13. And the tangent of theta compares the opposite to the adjacent. Tangent is the one that leaves hypotenuse out of the problem. That would be 12/5. The way you can remember then your ratios for sine, cosine, and tangent is with the special word SOHCAHTOA. Sine opposite hypotenuse, cosine, adjacent hypotenuse, tangent, opposite, adjacent. SOHCAHTOA is your word. You want to learn it, and you want to make sure you can spell it. Now don't forget, we said there were 6 ratios. We haven't used the other 6 yet. But we do know that all 6 of them, or all 3 of these, I should say, are reciprocals of the original 3. So here I've written them. Each one the reciprocal of the one over to the left. So that's comparing hypotenuse to opposite, and hypotenuse to adjacent, and adjacent to opposite. The first one is the cosecant, abbreviated as CSC. Cosecant and sine go together. You would think cosecant, cosine, but no, cosecant goes with sine. Secant goes with cosine. So just remember, they're backwards. The one that makes sense is cotangent. Cotangent goes with regular tangent. So this is how you would find the 6 ratios in a right triangle. So how about you try it? See if you can write down all 6 of the ratios. You might be thinking, wait a minute, we're missing a side. Aha! We might have to do a little math to figure out what the third side would be. I know you remember this. You've seen it before. It's our friend, the Pythagorean theorem. We are missing the side adjacent to theta. And so we have to do a quick Pythagorean theorem in order to get it. So that side ends up being the square root of 72. And by simplifying, that's 6 root 2. Now we're ready to find the 6 ratios. SOHCAHTOA. Sine is opposite over hypotenuse, 3/9, which reduces to 1/3. Cosine is adjacent over hypotenuse. The 6/9 part can reduce to 2/3. Tangent is opposite over adjacent. I reduce the 3/6 to 1/2. But remember, we can never have a square root in a denominator. So what I'm going to do is multiply the top and the bottom by root 2. That makes the top root 2 and the bottom 2 times root 4, which is 2 times 2, which is 4. Now I need to get all the reciprocals. So I'm just going to take these and I'm going to find the reciprocal of each one. So for cosecant, that's 3. For secant, that's 3/2 root 2. But then I have to do the multiply top and bottom by root 2. And for tangent, I actually decided to go right here to my middle step. That should say cotangent. Oops, little misprint. And take this fraction and flip it upside down to root 2. So do make sure you change this to say COT or cotangent. Now you try. Pause the video and see if working with somebody nearby you can find all 6 trig ratios fully simplified. Pause now. We're back. Check your work. Oops, looks like once again I have a little mistype right there. That should have said cotangent, COT, not regular tangent. But take a look. Here are all the answers. Go ahead and pause for a moment so that you can look at all the answers, check them against your work, and make sure you understand where they all came from. All right, so the next thing we're going to tackle is what if instead of giving me a picture, I am just given a clue. I'm given one of the 6 ratios, and I'm supposed to use that to find all the rest? Is it possible? Of course it is. If the cosecant is 15/8, I know the sine must be 8/15 because these two are reciprocals of each other. Knowing that the sine is 8/15 means I can come over here and draw a right triangle. Sine is opposite over hypotenuse. So there's theta, there's 8, there's 15. Looks like I need to do some math to find that bottom side. So a little Pythagorean theorem later, and I get a lovely dimension of the square root of 161. So now let's go and do our work. Cosine, adjacent over hypotenuse, tangent, opposite over adjacent, and then multiply top and bottom by root 161. Now I just have to find the reciprocals of both of those. So the reciprocal for secant just means a quick rationalizing. And for cotangent, I'm not going to do the reciprocal of my final answer. I'm going to go back to the start because then the reciprocal is clean and done. So it's totally possible to find all the ratios given just one of them. Now how about you try? Here I'm going to give you the cosine of theta. Using that clue, find all the other ratios. Pause now and come back when you're ready to check your answers. And lo and behold, here they are. I went ahead and put adjacent over hypotenuse, my clue, and then I used the Pythagorean theorem to find the square root of 119. Then I was able to build all of my ratios and then find all of the reciprocals. That is the conclusion of today's part of right triangle trigonometry. Remember, we have way more to go, including figuring out what these numbers actually are used for. Good luck and have fun doing your homework.